We are pleased to introduce the Iwani Laboratories Group. The main purpose of our company's establishment is to create robot eyes using image recognition technology. Sometime after its establishment, we needed a world for the robot to operate in, so we began the process of building a parallel world within the web. This is about building a 3D space on the internet that is a copy of reality as it is, and creating a platform for the development of other activities such as information, economy and culture that are a counterpart to activities in the real world. This is exactly the same concept as the digital twin that we call now, which we have been conceiving and developing for 30 years. Now let us talk about how the CV method, 3D spatial information platform called Another Earth was created and how it is used. Here's a simple image of that. A series of services are already in place to generate CV video by processing the video through CV operations, uploading it to a server and distributing it from the cloud. In other words, we can say that the basic form of Another Earth has already been created. We believe that you could see the system is extremely easy to use with just a browser. Here are some CV images selected from our product ALV2. See stable image display with triaxial anti-shaking technology. The viewpoint can be switched in a 360-degree image. Smooth viewpoint changes are realized from up-down, left-right and up or downward. The camera's running trajectory can be checked in 3 dimensions. Then, return the viewpoint to the ground. 3D tags can be placed. Tags can be linked to any related information. You can place 3D models as tags. The measurement function can measure the latitude, longitude, and elevation of a single point on the Earth. It can measure length and height. Tags can link to any related information. It can also calculate the area. These are just a few of the many functions of CV video. What are the outstanding features of our CV method, 3D spatial information platform? High accuracy corresponding to the GSI's 1/500 scale plan preparation is achieved. Absolute accuracy is ±15 cm and relative accuracy is ±5 cm at 20 meters from the camera. The 3D display of the CV method has excellent realism because it uses the actual image as it is. It has the excellent feature of not missing any information, because it is the actual image. The feature that what is in the image is always real and what is not in the image does not exist seems simple, but it is an excellent feature that no other system has. This feature is an absolute prerequisite for management operations. A huge amount of data is compressed and delivered from the server. Users can use their own browsers, which reduces the cost of the system. The map is not CG, so there is no diagramming process. The excellent feature of the image becomes a 3D map as it is directly reflected, contributing to simplified processing, easy updating, and elimination of errors caused by diagramming process, thereby contributing to lower cost. Our group companies are eWinnie Laboratories, Limited, and Earth Data Company and the local subsidiary in Thailand. What is the role of each group company? The main body of eWinnie Research Institute, Incorporated, will concentrate on R&D, technology development, and product development, and continue to produce and accumulate intellectual property. Earth Data Company is a company dedicated solely to the realization of Another Earth. Another Earth will be deployed on the CV Method 3D spatial information platform. Since a large amount of capital is required for a global platform as well as a domestic one, as a publicly listed company including IPO, we will be the container of investment from our partners' companies and will make alliances including capital tie-ups. Local subsidiary in Thailand is, with Another Earth in mind, it serves as a factory to generate CV images and create a database by processing a large amount of images through CV operations. Here, we will show you the Another Earth in a very miniature size. This is the basic form of Another Earth. In between business operations, we've been driving a video shooting vehicle and collecting data of Japan and Thailand little by little. The blue areas on the map are locations that have already been photographed and processed. On the left, we have already photographed 22,000 kilometers on all national roads in Hokkaido and around the Yamano line in Tokyo. On the right, about 1,000 kilometers around Bangkok was taken by a local company in Thailand. Now, please take a look at some of things that can be done on Another Earth, and imagine what you would like to see in its completed form. You see this map in your browser now. We are expanding rapidly. Zoom in on the Tokyo area, zoom in further on the Ginza area, and click here around the Ginza 3-Chome intersection, jump to an image of that point. As you can see, the CV technology integrates images and 3D space on the time axis, sharing time and space as it is with live-action images, not CG. The image is taken by a full-dome camera, so you can see the entire 360-degree surroundings. Naturally, the bottom is also visible. The video shooting vehicle is erased by 3D processing, and the hidden road surface is reproduced. Streams allow for smooth movement through space. After this, try to measure the position of traffic signs. Click on a traffic sign to display location information. Latitude, longitude, and elevation are displayed here. Next, measure the height of the streetlight. Clicking on the highest point of this streetlight, we see that it is 8.47 meters from the road surface. Next, we measure the distance between the buildings across the street from each other. The distance in 3D space from here on this building to here on the opposite side of the building was displayed as 27.64 meters. Some measurements are highly accuracy as we told you before. The error is less than 15 centimeters in absolute accuracy and less than 5 centimeters in relative accuracy. Next, this is a very notable function. You can link and share various information in the database by pinpointing and tagging objects in the video. In other words, everything in the video becomes a platform for information. Let's try to tag it actually. Here it is. The title of the tag is Title 3D Tag. Since the tag is placed three-dimensionally, the tag points do not move even if the viewing position or orientation is changed. Please check it. And again, please note that all of these operations are done in the browser. Then, here are a few uses of tags. Document data. Here an example link to a streetlight ledger. Following is a link to a video of our automated driving experiment in Ginza. Next, we will fly through time and space and warp to a temple in Thailand. The tag also takes you to the GU website. Subway Ginza station photos have been registered. These tag information are shared globally in principle. In this way, various information on the internet, including time axis, can be linked to 3D spatial information. We have conducted a market size survey, assuming a market by another Earth. First, let's examine what GAFA is profiting from. Their main focus is on e-commerce and internet advertising on the internet. Our immediate goal is to create a business space on the another Earth as well. Infrastructure inspection, maintenance, and management is exactly what we have done and what we are good at. The application aspects are unlimited. We are convinced that the next generation will naturally shift to the CV method, because it is easy to process, distribute, and with no diagramming process, make it an excellent cost-effective solution for 3D maps for automated driving and other map-based industries. The market size of another Earth is so huge that it cannot be clearly defined, but it is expected not only to expand conventional industries, but also to create new industries one after another in another Earth, and economic activities will expand at once. We believe that the need for data platforms will increase in order to take advantage of the vast amount of digital data in the future. Within this context, we hope you understand that our another Earth is in an extremely advantageous position because the CV images are intact under the digital twin itself. Therefore, we believe that it can not only meet the needs of the platform of the future, but can also be a high-level platform that integrates all of the multiple useful data platforms that will be developed in the future. We think it is particularly compatible with many spatial information such as the metaverse that is now being developed around the world. There, new data value will be created through integration, and it is expected to be used not only for data retrieval and browsing, but also for various social experiments and simulations, as well as for economic and cultural activities. Next, we would like to talk about patents and intellectual property related to the many new technologies, such as the CV method, that have created another Earth. The Japan Patent Office has taken the lead in evaluating and preparing a business feasibility evaluation report on the intellectual property status of small and medium-sized enterprises nationwide. Evaluation items are market trends, intellectual property ownership, evaluation of technical capabilities, value evaluation, etc. The perfect score of 30 points, the company received 27 points. Iwani Laboratories, Limited, was rated first in the nation. Here is a real comment from the surveyor of the survey firm that actually conducted this survey. Though it was the most advanced and difficult content of the 150 or so SMEs we visited across the country, more I learned, the more I realized that Iwani Laboratories' technology is simply amazing. We have received such compliments. Following is a list of major patents held by our company related to this business. We currently hold about 20 patents. Patents cover a wide range of fields from the basics to applications, such as 3D spatial recognition, high-precision 3D maps, self-localization, automatic driving, automatic recognition and positioning. From this, you could see that CV technology can become a global platform as a purely domestic technology. From now, we present the main results of the Mobile Mapping System, MMS, using images along a timeline. More than 30 years ago, We had created the prototype of the current system and had a 72% share of the MLIT market. At that time, it was a two-dimensional video GIS system, not yet a three-dimensional one. Here is the system that was used at the National Road Office. Following is a business that we received the order by Roads Department, Hong Kong after we exhibited at an exhibition in Beijing, China, 12 years ago. Until then, they had been managing their facilities using 2D maps, but the system was introduced to use this measurable image to check because they didn't recognize if there is really object there, or if they have not been relocated, or if there are no missing parts. It was started from 2013. We have built a database extension 6,500 kilometers. Here is an introductory video. Let's begin with a description of the dynamic view. Switching resolution, streaming. 360 degrees view. Zoom. Third view. Jump and move. This is tagging. Among the various functions, tagging function has been particularly well received by users. This is 3D measurement. The area of the signboard is measured. It measures the distance between buildings. This is by importing data from ArcGIS. The imported coordinates are displayed in the image to check if the object is really there or not misaligned. Two sets were delivered to the Science and Technology Agency in Saudi Arabia. Their request was to create an original street view. Next is Department of Rural Roads, Thailand. We sold the equipment and software to them and they built the DB. We had been videotaping 50,000 kilometers of local roads for 3 years. A total of 150,000 kilometers of data was maintained. As a result, amazingly, by pre- and post-implementation measures taken, system installation each time reduced the number of accidents by 91% and the number of fatalities by 90%, and we awarded an honorary award in the International Road Federation for the road safety category in 2020. This is a joint development with Canaan Georesearch, Limited. This is a subsurface survey system that investigates cavities and buried pipes under the road surface. Underground cavities and buried pipes are found by driving a vehicle equipped with a special ground-penetrating radar. However, it is difficult to record accurately its coordinate position on the ground. By combining our system with this, it is possible to identify the location of them easily by comparing it with the location above ground. This is a driving simulator using live-action video jointly developed with Toyo Technica. Features include not only the camera's point of view at the time of shooting, but also the ability to play back images that include lane changes through 3D processing. The viewpoint position follows the steering wheel operation. We mainly sell our products to automobile companies, who use them to verify the functionality of ADAS cameras for automatic driving during pre-shipment inspections. Jake's work in Colombo. It was used for a preliminary survey before the introduction of the new transportation system. System was completed through joint research with the Metropolitan Police Department. When a traffic accident occurs, they go to the scene to investigate the accident, which often involves traffic control. Traffic restrictions can take up to 3 hours in some cases, and have become a social problem that causes traffic congestion. The system has been using to conduct this traffic accident investigation in a short time. With this system, traffic control is not necessary, or if it is, It is only required for a short period of time, since the vehicle is simply driven around the scene. We have received high evaluations from customers who say that the normal 3-hour traffic control only takes 15 minutes. Data acquired must also be accurate drawings that can be used in court, and this requirement is also satisfied. Department in charge received the Superintendent of Police Award and the Director General of the National Police Agency Award. This is a general-purpose version of the system for the Metropolitan Police Department, as we mentioned earlier. Feature is that the camera is equipped with a laser, and the image and laser point cloud can be taken together, and the camera and laser are calibrated. This is the optional laser point cloud. The point cloud is marked with the corresponding image. This is a video taking of the road in front of our workplace. We add the background of the image to this point cloud, we get something like this. Here is a highly accurate ortho image. Zoom in. As the CV images show reality without lies, of course it is captured as it is, if a paper cup is there like this. This means that even the things left behind of the accident scene are captured as they are. As we checked the width of the 45 cm white line of the stop line, it was exactly 45 cm wide. Using the semantic segmentation method to paint each landmark in an image, such as trees or roads, and then extracting the point clouds that hit the color clusters, a polygon of the landmark can be created. Here is an example of installation at Nexco East Japan. This is the smart maintenance highway proposed by Nexco East Japan. Our system has been used by Nexco East Japan to shoot and process extension 15,000 km of the extension 3943 km highway managed by Nexco East Japan, and to build a 3D spatial information infrastructure. The system has been highly evaluated, especially for its ability to be operated from ordinary terminals on the network and for its ease of use from a browser. We are about to show you are. The first half is a joint research project with Tokyo University of Marine Science and Technology. The theme of the project is automated maps for ships and river facility management. In the second half, we will introduce the systems for power pole management, facilities, patrols, and inspections for electric power companies. The purpose of this project is to improve the efficiency of patrols, inspections, and operations by using AI to make image judgments. This is the Ninebashi River. It is equipped with an all-sky camera as in the case of road, so you can see all the surroundings. By giving coordinates from the outside, a highly accurate 3D map of the river can be created, even in places where GPS is not available, such as a highway above a river. In order to make effective use of this system, not only automatic driving, but also 8K camera attached to take high-resolution images of parts of the facility to enable detailed checks of the facility. Here, this system is designed for electric power companies. Electric power companies are attaching 8K cameras to utility pole management. The left half of the image here is the 8K camera image. You can see the details of the poles. So, by selecting the Transformer to view, you can view images from multiple angles at the same time like this. We are currently installing 6 8K cameras on an experimental basis to obtain more detailed images. Let us briefly explain about types of MMS equipment and peripheral equipment. That the basic configuration is a full dome camera, GNSS, and a vertical meter, but these do not include a laser scanner. Basic functions of our MMS are image-based and complete. Laser scanner, high-precision GNSS, IMU, 8K camera, etc. can be installed as options. The IMU provides navigation prediction in areas where GNSS satellites cannot be received, such as tunnels. Here is an example of an optional vehicle equipped with a laser and high-precision GNSS IMU, as well as an 8K camera. The word CV has probably already appeared many times, but let us explain the principle again here. Basically, we use a full dome camera and it typically takes shoot at a frame rate of 15 to 30 to acquire spherical images. These are expanded into equidistant cylindrical projection as image processing. Now, let us explain through the video how to precisely determine the position and orientation of a moving camera. A number of feature points are extracted from each frame image, and the motion of these feature points is tracked across frames. The blue dots are feature points and the ID numbers of the feature points are indicated next to them. Then, these feature points are tracked to obtain the three-dimensional positional relationship of each frame using a CV calculation tool developed by our company. Specifically, for each frame, information on the camera position and posture, X, Y, Z and yaw, pitch, roll, at the time of shooting are acquired. The chain of lines created by each of these spheres is the camera trajectory, with the center position of the sphere indicating the camera position, XYZ, and the beard-like object protruding from the sphere indicating the axis of rotation, yaw pitch roll. Each video frame has 6 variables for its camera position and posture due to the CV operation we described. By automatically tracking common feature points across multiple frames and triangulating the rest, the 3D coordinates of any point in the image can be attained. This is the measurement accuracy using a full dome camera, specifically the Ladybug 3. This is the case with GNSS. Is the case where no GNSS is used and 1 GCP is placed every 100 m. This coordinate is generally within 7 centimeters. Mentioned above, it has the surveying accuracy for the GSI's 1500 plan preparation. I've just introduced an example of using a larger camera called a Ladybug, but a smaller camera like this can also be used if you don't mind reducing the accuracy. Is an example of a small camera in use. We provided a system to Izumi City in Chiba, which is a sample district for disaster prevention, for the construction of a disaster prevention system. The drone is not equipped with GNSS, it does not have direct location information. However, by first acquiring an image and sharing the feature points of the image of a car driving down along the road with the drone's image, the drone's image can also be converted to a CV image. In other words, it is possible to generate an image that can be measured in the same way as on the ground. Is taken by this drone. On the ground, the tracks taken by the vehicle are displayed. Click on the vehicle track to jump there. Also, clicking on the drone's trajectory will jump to that location in the air. Meantime, here is a photo taken on the premises of the Geoinformatics and Space Technology Development Organization, GIDS, in Thailand. Here are the MMS vehicle and drone used for the video shoot. First is the CV image from the car. The trajectory of the drone is visible in the air at the same time as the trajectory of the car on the ground. On the drone track jumps to that location in the air and switches to the video from the drone. This is another CV image with a 360-degree view. The drone is filming at 3 different heights. Here is an image at a height of 30 meters. Clicking on the trajectory in the air jumps to a height of 60 meters. Furthermore, clicking on the trajectory in the air will jump to a height of 100 meters. On the ground and take measurements. The distance between this building and this tree is measured at 32.66 meters. Jump to the drone's trajectory and you can see the measurement location from the air. Video was taken at the Fukushima robot test field. It integrates walking, drone, and car footage. The trajectory of the shooting is now displayed. It is a walking shot and the photographer's blue helmet is visible. From the drone, we go down to the road by the shooting vehicle and take a look. This is a 6-story plant. There are many shooting tracks inside the building. Let's go inside and take a look. Introduce 3D CG creation as an example of the use of CV video. SCOV images are measurable images. Multiple points can be surveyed to create a 3D CG model. It can be replaced with a high-resolution texture later. It can be replaced with a high-resolution texture later. The images of Apex, the Venu 4G8, and its surroundings were created from aerial and ground shots, and 3D CGs were created from each to create a composite. Simulation is possible by hiding the 3D model in the background of the CV image. For example, the location is Otaru, and the river here is the Otaru Canal. This is a tsunami simulation. The water level is shown in the lower right corner. A tsunami climbs up the slope of Otaru. Is the CV footage itself, taken immediately after the Great East Japan earthquake. It turns out that it is most appropriate to see this in a CV image, with no lies. All the objects in the picture are reality itself. Take this as a hint for disaster preparedness. Can we think of a platform like this? Local government in the region will take video from normal times and provide a web service as a 3D GIS as a service to residents. And if, unfortunately, a disaster occurs, emergency operations will be performed within this web. It can be used as a public service in emergency situations, taking advantage of 3D spatial information. After a disaster, the system can reshoot the site to detect the disaster area, quickly respond to the disaster and plan for recovery, and save a record of the entire recovery work process. Since CV technology can process images in 3 dimensions, it is possible to display special images that are unique to CV. Here are some examples. And CV images always have 3D coordinates, and 3D measurement is possible within the image. A 3D map, that is, dynamic map, can be created by making 3D measurements within the CV image. This is a map created from images, so it matches the image perfectly. By using recognition and positioning technology together, it is possible to determine the attributes of landmarks and signs while recognizing them, and to perform 3D positioning, making it possible to automate a significant portion of the process.